What if every single moment of your life, every choice you've ever made, is not just a single path you've traveled, but one branch on an infinite tree of possibilities? What if every time you decided to turn left or right, to speak up or stay silent, the universe itself split in two, creating two separate realities where both outcomes exist? This isn't science fiction. It's a mind-bending idea rooted in real physics, known as the many worlds interpretation of quantum mechanics, and it raises a startling possibility. Our universe might not be a singular, stable entity, but a constantly multiplying reality, bubbling and branching with every passing moment. At the heart of this astonishing idea is something called quantum bubbles, tiny, fleeting fluctuations in the fabric of space-time that could, under the right conditions, give birth to entirely new universes. Think of it like this: the cosmos might not be a still pond, but a simmering pot, always on the verge of boiling over with new realities. And what if, just what if it's happening right now, all around us, completely unnoticed? What if, even as you watch this, the universe you thought you knew has just split again, spinning off another version of everything, including another version of you? That feeling, the shiver of wonder, the dizzying sense of possibility, is where our journey begins. Together, we're going to explore one of the greatest mysteries in modern physics. We'll dive into the strange world of quantum mechanics, where particles exist in multiple places at once and reality itself is built on uncertainty. We'll ask whether our existence is far stranger and more magnificent than we ever imagined. And along the way, we'll uncover what it truly means to live in a cosmos that might be endless, branching, and alive with possibility. So settle in, open your mind, and let's venture into the unknown. To grasp how such a split could even be conceivable, we need to venture into the bizarre and beautiful rules that govern the universe at its smallest scales. This is the domain of quantum mechanics, and it operates in a way that feels completely alien to our everyday experience. In our macroscopic world, objects seem solid and predictable. A dropped cup falls to the floor and shatters. A car is either in your garage or it isn't. But zoom into the level of atoms and electrons, and this certainty evaporates, replaced by a realm of pure potential. The cornerstone of this quantum weirdness is a principle called superposition. Simply put, a particle like an electron isn't confined to a single location or state. Instead, it exists in a blur of all its possible states simultaneously. Think of it not as being in one place, but as being smeared out across a spectrum of probabilities, a cloud of could be. An electron isn't simply here or there. It is, in a very real sense, both here and there at the same time, existing in a blend of all possible positions until we decide to look. This blend of possibilities is described by what physicists call the wave function, a mathematical equation that encapsulates everything that could be true about the particle. This leads us directly to the second and perhaps most famous quantum puzzle, the measurement problem. What happens when we finally look? The moment we observe or measure this particle, something inexplicable occurs. The spread-out cloud of possibilities seems to instantly snap into a single, definite reality. The electron chooses a single location. This sudden jump from a multitude of maybes to one concrete answer is known as the collapse of the wave function. It's as if the mere act of looking forces the universe to make a choice. But here's the million-dollar question that has divided physicists for nearly a century. What is that choice, and what really causes the collapse? The traditional or Copenhagen interpretation suggests that the act of observation by a conscious observer is what forces this decision, creating one reality from the soup of potential. It's a neat solution, but it feels deeply unsatisfying to many. It places human consciousness at the center of the universe in a way that feels almost mystical, and it leaves us wondering what constitutes an observation in the first place. Does it require a human, a cat, a camera? This is the core of the measurement problem, the unsettling lack of a clear, objective line between the fuzzy quantum world and the sharp reality we perceive. This is precisely where the many worlds interpretation offers its radical alternative. It proposes a breathtakingly simple yet vast solution. The wave function never actually collapses. There is no choice. Instead, at the moment a quantum event has multiple possible outcomes, the universe itself splits. Every single possibility encoded in the wave function becomes real, but in its own newly formed, separate branch of reality. In one universe, the electron is detected here. In another, equally real universe, it's detected there. The entire cosmos divides, and each new branch continues on its own path, completely unaware of the others. There is no need for a mysterious collapse because every potential outcome is realized somewhere. It suggests that the reality we experience is just one thread in an unimaginably vast and ever-growing tapestry of existence. This brings us to the brilliant and for decades deeply controversial mind of Everett III. In 1957, as a young physics doctoral student at Princeton, Everett was profoundly dissatisfied with the Copenhagen interpretation's reliance on a vague, external observer to collapse the wave function. He saw it as an incomplete patch on an otherwise elegant set of equations. His radical proposal, presented in his doctoral thesis, was this: what if we take the mathematics of quantum mechanics completely at face value? What if the wave function doesn't collapse at all, but simply continues to evolve forever according to its own deterministic laws? This straightforward mathematical fidelity leads to an astonishing cosmological conclusion. Everett argued that when a quantum system interacts with its environment, be it a measuring device, a cat in a box, or a human being, it doesn't pick a state. Instead, the entire system becomes entangled. The observer becomes linked with the observed. In one branch of this newly entangled reality, the observer finds the electron here and has the experience of having measured it here. In another perfectly valid branch of the same universal wave function, that same observer finds the electron there and has a completely different memory of the event. Both outcomes are equally real. They simply cease to interact with each other. There is no collapse, only a perpetual splitting of reality into non-communicating branches. This is the heart of the many worlds interpretation. It's crucial to understand that these aren't worlds far away in some other dimension. They are all right here, superposed with our own, but we are, in a sense, trapped on our own branch. Think of reality not as a tree growing new limbs, but as a rope fraying into countless separate strands. Each strand is a complete, consistent universe, unspooling forward in time. Its inhabitants completely unaware of the other strands because every decision, every memory, every particle in their world is consistent with only one history. The you in this branch remembers turning left at the intersection. The you in another branch has an equally vivid memory of turning right. Both memories are real and true within their own branches. This solves the measurement problem with elegant brutality. It removes any special role for consciousness or observation. A split occurs not when a human looks, but whenever a quantum event becomes amplified to a macroscopic scale. When the fate of an electron decides the fate of a Geiger counter, which then decides the fate of a cat, and so on. The universe is splitting all the time, everywhere, with dizzying frequency. Every quantum event with more than one possible outcome, and that's nearly all of them, triggers a new branching. This means the number of parallel universes is not just large, it's truly infinite, with new ones budding off every nanosecond. Yet if the universe is constantly branching, where do these entirely new, disconnected universes with their own unique laws come from? To answer that, we must shift our gaze from the splitting of worlds to the very birth of reality itself and the concept of quantum bubbles. This idea takes the weirdness of the quantum world and scales it up to a cosmic level, suggesting that our entire universe might be just one bubble in a vast, frothing multiversal sea. At the subatomic level, empty space is not truly empty. It's a seething, turbulent foam alive with fleeting energy fluctuations. Particles and antiparticles constantly pop into and out of existence, borrowing energy from the vacuum for an unimaginably short moment before annihilating each other and returning it. This chaotic, energetic dance is what physicists call the quantum foam. It's the fundamental baseline of reality, and it's within this foam that the seeds of new universes may be sown. A quantum bubble or vacuum bubble is a particularly large and stable fluctuation in this foam. Imagine a pot of water just beginning to boil. Tiny bubbles of vapor form on the bottom. Most collapse almost instantly, but if conditions are just right, if the water is hot enough and the bubble is big enough, it can detach and rise to the surface, expanding as it goes. In the quantum foam, a similar process might occur. Through a random, incredibly rare fluctuation, a pocket of space could tunnel into a different, more stable energy state. This pocket would be a quantum bubble, a region of space with fundamentally different properties from the space surrounding it. This is where the concept of inflation becomes crucial. Most cosmologists agree our universe underwent a period of exponential expansion just after the Big Bang, a process called cosmic inflation that smoothed and stretched the fabric of space-time. A quantum bubble that forms with the right conditions could trigger its own inflationary phase. The energy difference between the inside of the bubble and the outside vacuum would act as a powerful repulsive force, causing this new region of space to expand at a staggering rate, potentially inflating into an entire, full-fledged universe within a fraction of a second. The truly mind-bending consequence is that this new bubble universe would be completely disconnected from our own. It would pinch off from our space-time, forming its own isolated cosmos. And because it originated from a random quantum fluctuation, the fundamental constants that govern it, the strength of gravity, the mass of an electron, the number of spatial dimensions, could be entirely different. In this cosmic landscape, known as the eternal inflation multiverse, our universe is just one bubble among an infinite froth of others, each with its own unique and randomly selected set of physical laws. Some might be barren, with forces too weak to form atoms. Others might be so unstable they collapse moments after forming, and a fortunate few, like ours, would have just the right Goldilocks combination to allow for galaxies, stars, planets, and life. So if the universe is constantly splitting, creating an infinite number of copies of itself, why don't we notice it? Why does our reality feel so solid, singular, and continuous? The bridge between the bizarre quantum realm and the stable world we perceive is built on a process called quantum decoherence, and it is arguably the most important concept for understanding how many worlds could actually work. To grasp decoherence, let's return to that blurry, spread-out particle in a state of superposition. It exists in a combination of states, like an electron being both here and there at the same time. This state is delicate, a coherent overlap of possibilities, but a particle is never truly isolated. It is constantly bumping into, interacting with, and being influenced by its environment, a stray photon of light, a molecule of air, the electromagnetic field. Each of these tiny interactions is like a tiny, inadvertent measurement. The environment effectively sees the particle. When this happens, something profound occurs. The particle's once coherent superposition, its delicate dance of both/and, begins to leak information about its state into the surrounding environment. This information becomes scrambled and dispersed among countless other particles, and it becomes practically impossible to ever gather it all back together. The superposition doesn't vanish or collapse. Instead, it becomes delocalized, spreading out so thoroughly across the environment that the individual states within it can no longer interfere with each other. They effectively lose their quantum connection, becoming separate and independent. This loss of quantum coherence is decoherence, and it happens almost instantaneously for any object larger than a few atoms. This is the mechanism that explains why we don't see cats that are both alive and dead, or cars that are both in the garage and on the road. A macroscopic object is so enormous, composed of so many trillions of particles constantly interacting with the environment, that it undergoes decoherence faster than the blink of an eye. The different possibilities encoded in its wave function don't vanish, they simply decouple from one another. From the perspective of any one branch of any one set of consistent environmental records, including your own memories, it appears as if a single, definite outcome has occurred. The other possibilities are still there, but they are now part of other, separate branches of reality that you can no longer access or detect. Decoherence is the process that irreversibly separates the branches of the universal wave function, creating the illusion of a single classical reality from the underlying quantum soup. This process is deeply tied to another quantum phenomenon, entanglement. We often hear entanglement described as spooky action at a distance, where two particles become linked so that affecting one instantly affects the other, no matter how far apart they are. But a more modern and perhaps more accurate way to view entanglement is as a correlation, a shared existence where the properties of one particle are inextricably linked to the properties of another. Entanglement is the engine of the split. Imagine a simple quantum event, a single radioactive atom that has a 50% chance of decaying within 1 hour. According to many worlds, the atom enters a superposition of decayed and not decayed. Now, introduce a Geiger counter designed to click if it detects a decay. When the atom and the Geiger counter interact, they become entangled. The combined system is now in a superposition. Atom decayed and Geiger counter clicked, and atom not decayed and Geiger counter silent. The two possible outcomes are now woven together. The process continues. A scientist enters the lab to read the Geiger counter. Her eyes, her optic nerves, and her brain now interact with the counter. She, too, becomes entangled with the system. The superposition now encompasses her own conscious experience. In one branch, she sees the counter has clicked and has the memory and belief that the atom decayed. In the other branch, she sees a silent counter and is certain the atom did not decay. From her perspective inside one branch, her reality is perfectly consistent and singular. She has no awareness of her other self in the other branch because decoherence has permanently severed the quantum link between them. The entire universe has effectively split along that fault line, with two copies of the scientist now inhabiting two separate, non-communicating realities. The sheer scale of this branching is almost impossible to comprehend. It's not just happening in laboratory experiments, it's happening everywhere all the time. Every time a photon bounces off a surface, every random quantum fluctuation in a sunbeam, every unpredictable mutation in a strand of DNA driven by a quantum event, each of these is a potential branching point. The number of new universes budding off from our own is not just large, it is incomprehensibly vast, growing at a rate that dwarfs the number of particles in our observable universe. This isn't a theory of occasional duplication. It's a theory of a reality that is perpetually, furiously, and infinitely multiplying. This constant, invisible branching raises a fascinating question. If we can't perceive these other worlds directly, is there any tangible evidence that they exist? The answer, surprisingly, lies not in finding a doorway to another universe, but in the undeniable strangeness of laboratory experiments that only make sense if we accept that reality is far more fluid than it appears. The evidence for this quantum weirdness, the foundation upon which the many worlds interpretation is built, comes from several iconic experiments that have consistently baffled and astonished physicists for decades. Perhaps the most famous and elegantly simple of these is the double-slit experiment. At its heart, it's a straightforward setup. A source fires particles, like electrons or photons, toward a barrier with two thin, parallel slits cut into it. Behind the barrier is a detector screen that records where each particle lands. If you were to fire tiny bullets at such a barrier, you'd expect to see two distinct clusters on the screen behind the two slits. But when you fire individual particles one at a time in the quantum world, something utterly bizarre happens. Instead of two bands, an interference pattern emerges, a series of light and dark stripes that is the unmistakable signature of a wave. It's as if each individual particle is passing through both slits at once and interfering with itself, a phenomenon that is only possible if the particle exists in a superposition, taking multiple paths simultaneously. Now, the real mystery deepens when you try to catch the particle in the act. If you place a detector at one of the slits to see which path it actually takes, the magic vanishes. The moment you observe the particle's path, the beautiful interference pattern disappears. The particles suddenly behave like well-behaved little bullets, forming two simple bands on the screen. The act of measurement, of asking a simple which-way question, forces the particle to choose a single path and destroys the wave-like behavior. The Copenhagen interpretation says this is the wave function collapsing due to observation. But the many worlds interpretation offers a different story. The universe splits. In one branch, the particle goes through the left slit and is detected doing so. In another branch, it goes through the right slit and is detected there. Both events are real, and the interference pattern is lost because the two histories can no longer interact. They have decohered. This leads us to an even more mind-bending variation, the quantum eraser experiment. This brilliant setup seems to play tricks with time itself. Imagine conducting the double-slit experiment, but now tagging the particles with a kind of quantum label that, in principle, could tell us which path they took, but without actually looking at the label right away. As expected, because the which path information exists, even if it's unread, the interference pattern vanishes. The particles act like particles, but here's the incredible part. If you later erase that path information after the particles have already hit the detector screen, the interference pattern miraculously reappears when you analyze the data in a specific way. It's as if the decision to erase the information in the present changes how the particles behaved in the past. The many worlds interpretation avoids this paradoxical backward-in-time influence. It explains that the erasure procedure doesn't change the past but rather correlates the present data with specific branches of the wave function. When you sort the data from the detector after erasing the information, you are effectively filtering out the results from only those branches where the interference effect is visible. The other branches where no interference occurred are simply sorted into a different dataset. The experiment doesn't rewrite history. It just allows you to see the consequences of a particular set of branching histories, confirming that the superposition and interference were always there, just entangled across multiple realities. Beyond these classic tests, recent advancements continue to push the boundaries of what we thought was possible, further challenging our classical intuitions. Scientists have now performed the double-slit experiment with increasingly large molecules, and the interference pattern persists, demonstrating that quantum weirdness is not confined to the realm of tiny particles. Furthermore, the successful creation of Schrödinger's cat states in laboratories not with actual cats, but with tiny drums or electrical circuits placed in a superposition of vibrating and not vibrating, provides direct evidence that superposition is a real, physical state that can be engineered and measured, even for objects visible to the naked eye. These aren't just thought experiments anymore, they are tangible demonstrations that the quantum world of both/and is the true foundation of our reality, and the classical world of either/or is a persistent illusion created by decoherence. Each of these experimental results is a silent witness, pointing toward a cosmos that is vast, interconnected, and teeming with possibilities far beyond our everyday perception. To understand how these fleeting quantum events could give rise to entire cosmos, we must explore one of the most powerful ideas in modern cosmology, the theory of cosmic inflation. This concept suggests that our universe underwent a period of staggeringly rapid expansion just moments after its birth, a growth spurt so extreme it helps explain the large-scale structure and uniformity we observe today. But inflation might not be a one-time event that happened to our universe alone. Many theorists now believe it could be an eternal process, constantly creating new regions of space-time in a forever expanding multiverse. This is where the humble quantum bubble becomes a cosmic genesis engine. Imagine the fabric of space-time not as a serene, empty void, but as a kind of energetic field, much like an ocean. In some regions, this field might be in a high-energy state, a condition that generates a powerful repulsive force, causing space to expand at an exponential rate. This is the inflaton field, the driver of cosmic inflation. Now, within this raging inflationary sea, random quantum fluctuations can cause tiny pockets of this field to suddenly tunnel into a lower, more stable energy state. It's akin to a bubble of vapor forming in a pot of boiling water. This transition releases energy and causes that specific pocket of space to stop inflating violently and instead settle into a more sedate expansion, forming what we would recognize as a stable universe, a hot, dense soup of particles that will eventually evolve into galaxies, stars, and planets. This stable region is a quantum bubble that has successfully nucleated. This process suggests a breathtaking possibility. Our entire observable universe, with its hundreds of billions of galaxies, may be contained within just one such bubble that nucleated long ago from a much larger and eternally inflating background spacetime. We are living inside a cosmic bubble, and if it happened once, there is no reason it wouldn't happen again and again and again. The eternally inflating background continues its frantic expansion, and within it, countless other quantum bubbles are constantly popping into existence, each pinching off to become its own separate, isolated universe. This is the concept of the inflationary multiverse, a vast and frothing foam of universes, each with its own unique history and properties. This leads to one of the most profound implications of this theory, the variation of physical laws. The random quantum fluctuation that triggers the formation of a bubble universe also determines the specific properties of that new cosmos. The fundamental constants, the strength of gravity, the mass of an electron, the number of spatial dimensions, could be frozen in during this transition. In this cosmic landscape, our universe isn't special. It's just one possible outcome in a vast lottery. Some bubbles might have gravity so strong they collapse back in on themselves instantly. Others might have forces too weak to ever form atoms. A small fraction, by pure chance, would have the precise Goldilocks conditions necessary for complexity and life to arise. This concept of an anthropic selection effect offers a potential explanation for why our universe seems so finely tuned for our existence. If it weren't, we simply wouldn't be here to ask the question. The bubble universe idea provides a powerful physical mechanism for the endless branching predicted by the many worlds interpretation. While many worlds describes the splitting of our own universe into branches with the same fundamental physics, eternal inflation describes the creation of entirely new universes with potentially different physical laws. Together, they paint a picture of a reality that is not just branching, but also constantly birthing new realms of possibility in a multiverse of unimaginable diversity and scale. This ceaseless activity of the quantum vacuum is not just a curious sideshow. It is the very engine that could power the creation of entire cosmos. To understand how, we need to shift our perspective from the impossibly small to the unimaginably large. The same principles that allow a particle and antiparticle to flicker into existence for a fleeting moment might also, under the right conditions, allow a universe to do the same. The key lies in a special kind of quantum fluctuation that doesn't just create particles, but creates a fundamental shift in the fabric of reality itself. Imagine a particularly large and stable quantum fluctuation in this seething foam. Through a process known as quantum tunneling, a tiny region of space could randomly transition into a different, more stable energy state. This is analogous to a ball spontaneously rolling out of a small depression in a valley and into a much deeper, more stable valley far below, without having the energy to go over the hill between them. In quantum terms, it tunnels through the energy barrier. This newly transitioned pocket of space would possess entirely different properties than the space surrounding it. It would be a quantum bubble, a region of false vacuum that has decayed into a true vacuum. The energy difference between the inside of this bubble and the outside is what makes it cosmologically significant. This energy acts as a powerful repulsive force, causing the bubble to expand at an exponential rate. This isn't a gentle growth, it's an inflationary explosion, doubling in size incomprehensibly fast over and over again. In a fraction of a second, this microscopic bubble can inflate to a size larger than our entire observable universe. The energy that drove this expansion eventually converts into the hot, dense soup of particles that forms the starting point of a standard Big Bang. In this breathtaking scenario, a random twitch in the quantum foam gives birth to an entire cosmos, complete with its own space-time and potentially its own unique set of physical laws. This means our universe might not be a singular, lonely entity. It could be just one bubble in a vast, eternal cosmic foam, a multiverse where new universes are constantly nucleating, inflating, and pinching off from the eternally inflating background space-time. Each bubble universe would be completely causally disconnected from the others, forever beyond our observational horizon. Some might be stillborn, collapsing instantly. Others might be barren, with laws too hostile for any structure to form. And a rare few, through sheer statistical chance, would have the perfect Goldilocks conditions to give rise to galaxies, stars, planets, and life. We find ourselves in one of those rare, fortunate bubbles, living proof of the creative power hidden within the apparent nothingness of empty space. While the core idea of many worlds has been around for decades, it's far from a static concept. In recent years, a new generation of theoretical physicists has been refining the interpretation with powerful mathematical tools, moving it from a philosophical curiosity toward a testable scientific framework. At the forefront of this effort is Sean Carroll, a cosmologist at the California Institute of Technology. Carroll argues that we should take quantum mechanics utterly seriously, not as a problem to be solved by adding extra rules like wave function collapse, but as a direct description of reality. His work focuses on the nature of quantum entanglement and decoherence, providing a robust, modern foundation for how branching actually occurs. He emphasizes that the wave function is not just a calculational tool. It is a real, physical object, a field that exists in an abstract, high-dimensional space known as Hilbert space. The evolution of this universal wave function is what we experience as the flow of time, and its perpetual branching is the continuous creation of new realities. Carroll's approach is to demystify the process, showing through precise mathematics that branching is an inevitable outcome of particle interactions, not a magical duplication event. This push for mathematical clarity is shared by David Deutsch, a pioneering physicist at the University of Oxford and a founding father of quantum computing. Deutsch offers a compelling reason to take the many worlds interpretation seriously. It makes sense of the sheer computational power of quantum computers. A classical computer performs calculations one at a time in a single sequence. A quantum computer, however, leverages the principle of superposition. Its quantum bits or qubits can be in a combination of 0 and 1 simultaneously. Deutsch argues that when a quantum computer runs a complex algorithm, it is effectively performing calculations across a vast number of parallel universes. The final measurement we see in our branch is simply the result that is consistent with our history, but the processing power required to solve the problem was harnessed from the computational resources of an entire ensemble of worlds working in concert. For Deutsch, the existence of working quantum computers isn't just suggestive of many worlds. It is nearly direct evidence for it, as their operation is inexplicably powerful if confined to a single classical universe. Beyond these foundational voices, other researchers are tackling the interpretation's trickiest problems head-on. A major historical criticism has been the seeming vagueness of the branching process. Precisely when does a split occur? How many worlds are created? Modern work in decoherence theory has provided powerful answers. Researchers can now model how a quantum system interacts with its environment, calculating the exact rate at which quantum superpositions become irreversibly disconnected from one another. This isn't a philosophical debate anymore, it's a quantitative calculation. We can determine for a given system how quickly information about its state leaks into the surrounding environment and causes the different branches to decohere. This turns the splitting of worlds from a vague event into a precise physical process with a well-defined mathematical description. Another active area of research involves the thorny issue of probability. If every possible outcome happens in some branch, what does it mean to say that a particular outcome has a 90% probability? In a single universe, probability reflects uncertainty. But in many worlds, there is no uncertainty, everything happens. So how do we recover the standard, proven probabilistic predictions of quantum mechanics? Physicists are exploring sophisticated ideas centered on the structure of the wave function itself. One promising approach suggests that while all outcomes occur, they do not occur with equal weight. Some branches might be more numerous or have a greater amplitude in the wave function than others. From the perspective of an observer within a branch, this amplitude is experienced as the familiar probability. You are overwhelmingly likely to find yourself in a branch that aligns with the high probability predictions of quantum theory, simply because there are far more copies of you in those branches. This line of inquiry uses the mathematical tools of decision theory and self-locating uncertainty to show how probability naturally emerges from a deterministic, branching multiverse. The conversation is also expanding beyond the quantum realm to address the biggest questions in cosmology. Some theorists are exploring the deep connections between the many worlds interpretation and the theory of the cosmic inflation. They propose that the initial conditions of our universe, the very seeds from which galaxies grew, were themselves the result of primordial quantum fluctuations. These tiny ripples in the fabric of space-time, stretched to cosmic scales during inflation, determine the large-scale structure of everything we see. In a many-worlds context, this means that our entire cosmos, with its specific pattern of galaxies and voids, is just one possibility. Other branches of the universal wave function contain universes that started with slightly different fluctuations, leading to completely different cosmic histories. This merges the quantum multiverse with the cosmological multiverse of eternal inflation, suggesting a reality of literally unimaginable breadth, where every possible variation of physical law and cosmic history is realized somewhere in the grand ensemble of worlds. This ongoing research is transforming many worlds from a provocative interpretation of a laboratory experiment into a potential framework for understanding the origin and ultimate nature of everything. So if these branching realities are a fundamental feature of the universe, could we ever build a machine that actually harnesses their power? This isn't science fiction. It's the core principle behind the most revolutionary technology of the 21st century, quantum computing. To understand how it works, we need to move from theory to engineering and look at the remarkable device known as a qubit. In a classical computer, the fundamental unit of information is the bit. A bit is binary. It can be either a 0 or a 1, like a simple light switch that is definitively on or off. Every app on your phone, every website you visit, is ultimately built from vast sequences of these definitive zeros and ones. A quantum computer operates on a completely different principle. Its basic unit is the quantum bit or qubit. unlike a classical bit, a qubit isn't confined to a single state. Thanks to the principle of superposition, it can be in a combination of 0 and 1 at the same time. It's not that we don't know which state it's in. It genuinely exists in both states simultaneously, with a specific probability amplitude for each. Think of it not as a light switch, but as a dimmer switch that can be set to every possible setting between fully on and fully off all at once. This bizarre property allows a quantum computer to perform calculations in a way that seems almost magical. When you have two qubits, they can be entangled, meaning their fates are linked. This system of two qubits isn't just in one state. It can be in a superposition of four possible states: 0, 0, 0, 1, 1, 0, and 1, 1. With 3 qubits, it's 8 states. With just 300 qubits, the number of simultaneous states the system can be in exceeds the number of atoms in the entire observable universe. This is where the connection to the many worlds interpretation becomes so compelling. When a quantum computer runs an algorithm, it isn't performing one calculation at a time in a linear sequence. It effectively performs all possible calculations across all possible combinations of its qubit states at the same time. It's conducting a massive, parallel processing operation of unimaginable scale. Now the crucial question is, where is all this processing happening? From the perspective of the many worlds interpretation, the answer is breathtakingly literal. The different components of the qubit's wave function are processing information in different, non-interacting branches of reality. In one branch, a particular qubit is a 0, and that branch's version of the computer is working on that specific calculation path. In another branch, that same qubit is a 1, and that world's computer is working on a different path. The sheer number of these parallel computational worlds working in unison is what grants a quantum computer its phenomenal power. When we finally make a measurement to read out the answer, the wave function appears to collapse and we get a single result. But many worlds suggests we haven't collapsed anything. Our branch of reality has simply decohered from all the others, and we are left with the answer that is consistent with our specific history. The other branches with their different answers are still there, but we are no longer in contact with them. This provides a potential solution to one of the great puzzles of quantum computing. How does it actually work? If you were to ask a proponent of the Copenhagen interpretation, they might say the computer is exploring all possibilities in a nebulous realm of potentiality that collapses upon measurement. But the many worlds view offers a more concrete, almost engineering-level explanation. The computer is leveraging the physical resources of an infinity of parallel universes. Each universe tackles a different piece of the problem, and the final measurement reveals the solution found by the branch or ensemble of branches that successfully computed it. This isn't just a philosophical preference for pioneers like David Deutsch. It is the only interpretation that makes sense of the computer's operation. The staggering speedup offered by a quantum algorithm like Shor's algorithm for factoring large numbers isn't just a neat trick. It is direct evidence that the computer is doing something a single universe classical machine simply could not do. It is performing computations that would require more resources than exist in our one observable universe, strongly implying that those resources are being drawn from somewhere else from the vast ensemble of worlds that make up the multiverse. The implications of this extend far beyond raw calculation. If quantum computers work by tapping into the computational power of parallel realities, then they are not just tools for solving equations, they are our first true multiversal instruments. They provide a form of indirect empirical evidence for the existence of other worlds. We may never be able to visit these branches or communicate with our other selves, but we can build a machine that, by its very design and undeniable operation, relies on their existence to function. Every time a quantum algorithm successfully runs, it is a silent testament to the reality of the branching cosmos, a physical demonstration that our universe is far more strange, vast, and wonderful than it appears. This brings us back to that central, nagging puzzle we introduced at the very beginning, the measurement problem. Why is it that we, as conscious observers, only ever get to see one single, definite outcome from the quantum soup of possibilities? If an electron is truly in a superposition of spinning both up and down, why does our Geiger counter give one clear, unambiguous reading and not some blurry average of both? This is the core of the quantum mystery, the point where our comfortable classical intuition completely breaks down. The traditional Copenhagen interpretation offers an answer that many find deeply unsettling. It says that the very act of observation, of measurement by a conscious being, is what forces the wave function to collapse into a single reality. But this raises more questions than it answers. What exactly qualifies as a conscious observer? Is a cat conscious enough, a bacterium, a sophisticated computer? The line becomes impossibly blurry, and it places human consciousness on a mysterious pedestal at the very center of physics. The many worlds interpretation cuts through this philosophical knot with a solution that is both radical and breathtakingly simple. The wave function never collapses at all. There is no special role for consciousness, no mysterious trigger that forces the universe to choose. Instead, the answer is that we, the observers, are just as much a part of the quantum system as the particle we are measuring. When you measure that electron spin, you don't force it to choose, you become entangled with it. The entire system, the electron, the measuring device, and your own brain evolves into a superposition. In one branch of reality, the electron is spinning up, the device reads up, and you see it and form a memory of that result. In another, equally real branch, the electron is spinning down, the device reads down, and a different version of you sees that and forms a completely different memory. Both events happen, both outcomes are real. The only reason you, in this particular branch, are only aware of one result is because your conscious experience is inextricably linked to the specific branch you are on. You are trapped within a single, consistent history. This resolves the measurement problem by completely eliminating the need for a collapse. The mathematics of the wave function, which describes all the possibilities, just keeps on evolving smoothly and deterministically, exactly as it always has. The apparent collapse is not a physical event but a subjective one. It's the realization that our perspective is locked to a single thread in a much grander tapestry. We don't witness the branching itself because the moment it happens, our awareness splits along with the rest of the universe. The other yous on the other branches are just as real and just as convinced that their single outcome is the only one that ever occurred. This is why the universe feels solid and singular to us. It's not that the other possibilities vanish, it's that we lose access to them, forever separated by the swift and irreversible process of decoherence. The many worlds interpretation doesn't change the rules of quantum mechanics. It changes our understanding of what it means to be an observer within a quantum reality. This constant branching of reality forces us to confront some of the most profound questions about the nature of time and causality itself. In our everyday experience, time feels like a river flowing in one direction with a clear and unbreakable chain of cause and effect. You drop a glass, it shatters on the floor. The cause precedes the effect in a single, linear timeline. But if the universe is constantly splitting, this tidy model of causality begins to unravel in astonishing ways. The first major shift is in our understanding of time's arrow. In a single universe, the flow of time from past to future feels absolute. But in the many worlds view, the entire timeline might be better pictured not as a single line, but as a constantly widening fan or a tree with endlessly dividing branches. The past is not a single fixed point. It is the trunk of the tree from which all possible presents have blossomed. And the future is not a single destination, but the space where all of these new branches will continue to grow. Your personal experience of time is simply your journey along one specific branch of this immense tree. This radically changes the relationship between cause and effect. In a branching universe, a single cause doesn't have a single effect. Instead, one event at a branching point becomes the common cause for multiple, divergent effects, each playing out in its own separate reality. Imagine standing at an intersection, deciding whether to turn left or right. The cause, your decision-making process, is a quantum event in your brain. The effect is not one turn, but two. In the branch you inhabit, you turned left and encountered a specific series of events. But in another, equally real branch, the effect of that same cause is that you turned right, setting off an entirely different chain of consequences. Causality isn't broken, it's multiplied. A single moment of uncertainty creates a fork in the road of reality, and both paths are equally valid and real, each with its own complete and consistent chain of cause and effect from that point forward. This leads to the captivating and often misunderstood question of influence. If all these worlds are real, can they ever interact? Could an event in one branch somehow cause an effect in another? The resounding answer from the physics is no, and the reason is decoherence. Remember, when two branches split, they decohere. This means they lose their quantum connection and become completely separate and independent realities. They are like ships passing in the night that quickly sail so far apart they vanish over the horizon, forever out of communication. There is no known physical mechanism, no signal, no force, no particle that can travel between these decohered branches. The laws of physics that govern causality and the speed of light are local to each individual universe. An event in one branch cannot be the cause of an effect in another because there is no connective tissue between them. They are causally isolated. This strict separation is actually what protects the logical consistency of each individual world and prevents paradoxical nonsense, like a version of you from a branch where you won the lottery transferring the winning numbers back to your branch. However, this absolute separation opens the door to a different, more subtle way of thinking about influence, not between branches, but within the structure of reality itself. While branches cannot communicate after they split, they do share a common origin. All branches are part of the same universal wave function, which means that at a fundamental level they are still connected, even if that connection is no longer accessible to any inhabitants within a branch. Some physicists speculate that this underlying connection could, in theory, leave a faint imprint. For instance, if the wave functions of two branches were to somehow very briefly and weakly interfere with each other before they fully decohered, it might produce a tiny, statistically anomalous effect that could be measured. To date, no such effect has been conclusively found, and most consider it extremely unlikely, but the mere possibility highlights that the quantum world is still full of surprises. Our understanding of causality is not being overturned, but it is being expanded to a breathtaking scale, revealing a cosmos where the chains of cause and effect are not single threads but vast, intertwining webs of possibility. This dizzying vision of a branching multiverse inevitably pushes us beyond the equations of physics and into the deepest waters of philosophy, forcing us to reconsider the most fundamental aspects of our existence. If an infinite number of versions of us are living out every conceivable life path, what becomes of our cherished notions of free will, identity, and the very self? The implications are both liberating and deeply unsettling, challenging the core narratives we use to define our lives. Let's start with the classic philosophical puzzle of free will. In our everyday experience, making a choice feels like a genuine act of agency. You deliberate between two job offers, and it feels like you, your conscious self, are the one making the final call. But many worlds introduces a profound complication. It suggests that at the quantum level, your brain's decision-making process is subject to the same probabilistic rules as any other quantum system. The moment you make that choice, the universe splits. In one branch, you accept the job in New York. In another, you take the position in Tokyo. From a God's eye view outside the multiverse, both choices are made. This seems to suggest a shocking conclusion. You never actually choose one thing over another. Instead, every possible option is selected by some version of you in some branch. This is known as the illusion of free will. The feeling of choice is simply your conscious awareness traveling along one specific branch, unaware of all the others where different yous are having equally vivid experiences of making the opposite decision. Yet, many philosophers and physicists argue this isn't the death of free will, but a radical redefinition of it. Your will isn't free to alter the predetermined branching of the wave function. That process is mechanical and automatic. But your unique collection of memories, desires, and personality, the very thing you call you, is what determines which branch you find yourself on. Your choices are real because they define your path through the multiversal tree. The you who values adventure ends up on the branch where you moved to Tokyo. The you who values family stability ends up on the branch where you stayed home. Your internal state dictates your location in the multiverse. In this view, free will isn't about changing the future, it's about which future you get to experience. It's the difference between being the author of a single story and being a reader who always chooses the book that perfectly matches their tastes. This directly leads to an even more personal question. What happens to your identity when it is endlessly fractured? If there is a version of you who became a professional musician, another who became a surgeon, and another who never left their hometown, can we truly say they are all the same person? They share an identical origin, a common past up until the first moment their timelines diverged. But from that point forward, they accumulate completely different experiences, memories, and even physical changes. The musician's brain is wired for auditory creativity. The surgeon's hands have years of precise muscle memory. They become, for all intents and purposes, different people who simply started from the same point. The concept of a single, continuous self begins to dissolve, replaced by the idea of a branching identity, a vast family of selves, each with their own autonomy and narrative connected only by a shared root. This forces a stark confrontation with the nature of regret and significance. We often anguish over the path not taken, the what if of a different choice. But if many worlds is true, there is no road not taken. Every road is taken. The version of you that asked that person on a date is happily married to them in one universe. The version that didn't is contentedly single in another. This can be a source of immense comfort, as it suggests that no possibility is ever truly lost. Yet it can also feel strangely nihilistic. If every outcome happens, does any single outcome truly matter? The answer lies in shifting perspective from the multiverse as a whole to the individual experience within a branch. For that you reading this right now, your life is the only one you will ever know. Your joys, your sorrows, your loves, and your losses are utterly real and significant to you. The existence of other happy versions of you doesn't diminish your pain, just as the existence of other suffering versions doesn't invalidate your joy. Your branch is your entire reality, and the choices you make are paramount because they craft the only existence you will ever consciously experience. Finally, this framework offers a fascinating, if speculative, perspective on consciousness itself. The hard problem of consciousness, why and how physical processes in the brain give rise to subjective experience, remains one of science's greatest mysteries. Some thinkers, like David Chalmers, have pondered if the many worlds interpretation might provide a clue. Perhaps consciousness isn't a product that emerges from a specific arrangement of matter, but a fundamental property of reality. In this view, every branch of the wave function is experienced subjectively. Where there is a complex information processing structure like a brain, there is a rich, complex consciousness. Where there is a simpler structure, there is a simpler experience. This suggests that consciousness is not a single, continuous stream, but is itself branching and multiplying along with the physics, with each stream of awareness forever isolated within its own decoherent history. You are not a soul jumping between branches. You are the awareness inherent to this specific branch, and there are countless other awarenesses that were once you and are now their own distinct selves, all equally valid and real. This perspective doesn't solve the hard problem, but it expands its stage to a cosmic scale, suggesting that the mystery of experience is woven into the very fabric of a branching, bubbling, and infinitely creative multiverse. Despite its breathtaking elegance, Hugh Everett's theory was met not with celebration, but with a wall of dismissive silence and outright hostility from the established physics community. To understand why, we have to step back into the intellectual climate of the 1950s. The Copenhagen interpretation, championed by the towering figure of Niels Bohr, was not just a theory, it was the orthodoxy. It had been used to make incredible predictions and win Nobel Prizes. To suggest an alternative, especially one as radical as many worlds, was seen as heresy by many of the field's elders. The idea of an infinite number of real, branching universes struck them as the worst kind of metaphysical excess, a philosophical nightmare that violated the principle of Occam's razor by multiplying entities beyond necessity. They argued it was not science, but science fiction, an untestable, extravagant claim that solved the measurement problem by simply ignoring it and creating infinitely more problems in its place. The defining moment of this rejection came in 1959, when Everett traveled to Copenhagen to meet Niels Bohr himself, hoping to win over the architect of the very interpretation he sought to replace. The meeting was a disaster. Bohr and his circle of senior physicists were not just unpersuaded, they were openly antagonistic. They refused to engage with the mathematical core of Everett's thesis, dismissing it out of hand as a misunderstanding of quantum theory. They saw the notion of splitting universes as absurd, a ludicrously literal reading of the equations that ignored what they saw as the essential, paradoxical nature of quantum reality. For the young, confident Everett, this was a crushing blow. He had arrived with a revolutionary idea, born from a pure desire to take the mathematics seriously, and was met with the immovable force of scientific dogma. He left Copenhagen disillusioned, his spirit largely broken, and his career in academic physics effectively over before it had even begun. Following this defeat, Everett made a pragmatic and, for the world of physics, a deeply tragic decision. He abandoned his pursuit of a career in academia. Instead, he turned his formidable intellect to the burgeoning field of operations research and later to defense contracting, where he applied his skills in mathematics and complex systems to Cold War problems like nuclear weapons strategy and game theory for the Pentagon. He found success and financial security in this shadowy world, but he never fully let go of his physics. The many worlds interpretation was his child, and its rejection by the community he longed to be a part of left a lasting scar. He became somewhat reclusive on the subject, discussing it only with a small circle of friends and colleagues, watching from the sidelines as his life's most important work gathered dust on the shelves of university libraries. The theory might have been lost to history were it not for a handful of brave and open-minded physicists who, over the subsequent decades, began to see its profound value. The first champion was the legendary Bryce DeWitt at the University of North Carolina. In the late 1960s, DeWitt rediscovered Everett's thesis and was immediately captivated by its sheer logical power. He saw that it solved the measurement problem with a clarity and directness that Copenhagen could never match. DeWitt began teaching the interpretation in his classes and, crucially, gave it the name that would stick, the many worlds interpretation. He also connected with Everett directly, beginning a long correspondence that helped refine the theory and gave Everett a renewed, if cautious, sense of hope. It was DeWitt who pushed Everett to write a more accessible article for a broader physics audience, which was published in 1973 and helped introduce the idea to a new generation. Slowly, painstakingly, the intellectual tide began to turn, as physicists like DeWitt and later David Deutsch, John Wheeler, and others grappled with the persistent weirdness of quantum mechanics, they found that Everett's proposal, for all its strangeness, was the most coherent and paradox-free framework available. The development of decoherence theory in the 1970s and 80s provided the crucial mechanism that Everett's original work had lacked: a clear, physical explanation for how the branches split and why they become invisible to each other. This wasn't just philosophy anymore, it was hard physics that filled in the gaps. The rise of quantum cosmology, which sought to apply quantum rules to the entire universe, also made the Copenhagen interpretation's reliance on an external observer seem downright silly. Who was outside the universe to observe it and cause its wave function to collapse? Many worlds, which required no external observer, became the only game in town for cosmologists trying to model the birth of the cosmos. Tragically, Hugh Everett did not live to see his idea ascend to its current place of prominence. He died suddenly of a heart attack in 1982 at the age of just 51. In a final, poignant twist that seems pulled from one of his own branching realities, it is said that his ashes were interred according to his wishes with a copy of his seminal thesis. His daughter, Elizabeth, later revealed that he was a complex and often difficult man, who nonetheless believed until the end that the world would eventually come to understand his vision. He was right. Today, while far from universally accepted, the many worlds interpretation is a mainstream and respected position in quantum foundations, taught in universities worldwide and considered by many leading theorists to be the most likely candidate for the true description of reality. It stands as a powerful testament to a brilliant mind who was simply too far ahead of his time, and a sobering reminder that scientific progress often must wait for the old guard to step aside before a new paradigm can truly take root. The most persistent criticism leveled against the many worlds interpretation has always been its apparent untestability. If these other branches are forever beyond our reach, how can we ever claim this is real science and not just a fascinating philosophical speculation? This is a fair and crucial challenge, and while we may never build a device that lets us phone a parallel universe, physicists have devised several ingenious, albeit indirect, ways to search for evidence that our reality is not alone. One of the most promising avenues looks not into the quantum realm, but to the very edges of the cosmos itself. If the broader multiverse theory of eternal inflation is correct, the idea that our universe is one bubble in a vast, frothing cosmic foam, then it's conceivable that in the distant past, our expanding bubble universe might have gently bumped into a neighboring one. Such a collision would have left an indelible mark on the oldest light we can see, the cosmic microwave background radiation. This faint afterglow from the Big Bang is a snapshot of the infant universe, and cosmologists have meticulously mapped its tiny temperature variations. They are searching for a specific, anomalous pattern, a kind of circular bruise or a distinct gradient in the temperature that could be the cosmic scar of a bubble collision. While a few tentative candidates have been identified in the data, none have yet risen to the level of definitive proof. The search continues with increasingly precise satellites, a hunt for the ultimate cold case evidence written in the faint warmth of creation. Another approach leverages the strange connection between the many worlds interpretation and the rapidly advancing field of quantum computing. The sheer power of a quantum computer, as we discussed, is arguably evidence in itself. But we can push further. Researchers are designing specialized experiments that probe the precise boundaries of decoherence. The idea is to create larger and more complex systems that remain in a state of quantum superposition for longer periods of time. If the many worlds view is correct, the process of decoherence, where the environment measures the system and causes the branches to split, has a very specific mathematical signature. By meticulously comparing the observed rate of decoherence in these experiments against the predictions of many worlds and other interpretations, scientists can see which model best fits the data. It's a process of elimination, steadily ruling out alternatives until the only remaining explanation is the continuous, uncollapsing branching of the universal wave function. Perhaps the most daring and direct proposed test involves a concept known as quantum suicide, or its less dramatic cousin, quantum immortality. This is a thought experiment, not a real experiment anyone should ever try. Imagine a device is set up that is triggered by a single quantum event, like the decay of a radioactive atom. If the atom decays, the device releases a deadly poison. If it does not, the device does nothing. According to many worlds, at the moment of measurement, the universe splits. In the vast majority of branches, the atom decays and the experimenter dies. But in a small subset of branches, the atom does not decay and the experimenter survives. From the perspective of that surviving experimenter, they would witness a seemingly impossible sequence of events, the atom repeatedly failing to decay time after time against all astronomical odds. Their continued existence would be, to them, personal proof of the many worlds interpretation. Obviously, this is a macabre and utterly unethical idea, but it starkly illustrates a key difference in how probability is experienced from within a single branch of a branching universe versus a single, non-branching reality. The true path to validation likely lies in a convergence of evidence rather than a single smoking gun. As quantum computers become more powerful and their operation becomes inexplicable without appealing to some form of parallel processing, the case strengthens. As our maps of the cosmic microwave background become more detailed, we may yet find the faint imprint of a neighboring cosmos. And as our control over quantum systems improves, allowing us to create and maintain ever larger Schrödinger's cat states, we will be directly manipulating the branching process itself. We may not be able to visit other worlds, but by thoroughly understanding the physics of decoherence and the boundaries of quantum theory, we can infer their existence with ever greater confidence. The quest to test the many worlds interpretation is ultimately a quest to understand the fundamental architecture of reality, pushing the very limits of what is knowable through observation and reason. But what if entanglement isn't about a mysterious force acting across space, but is instead the ghostly, residual echo of a recent split in reality itself? This is where Einstein's famous spooky action at a distance takes on a completely new meaning within the many worlds framework. In a single universe view, entanglement is baffling because it seems to require instant communication, a violation of Einstein's cosmic speed limit that nothing can travel faster than light. How can one particle instantly know the state of its partner, no matter how far apart they are? The many worlds interpretation offers a radical solution. They don't need to communicate at all because their connection was forged not across space, but across the moment of their creation within the branching wave function. Consider the classic example of two entangled particles created together, perhaps from the decay of a single parent particle. They fly off in opposite directions, and we know that measuring the spin of one will instantly tell us the spin of the other. From the Copenhagen perspective, this is a moment of spooky, instantaneous collapse, but from the many worlds view, the moment those two particles were created, the universe itself split. In one branch, particle A has spin up and particle B has spin down. In another, equally real branch, particle A has spin down and particle B has spin up. The entanglement isn't a link that sends a signal. It's a permanent record of a shared origin, a correlation that was baked into the fabric of reality the instant those two branching histories separated. When a scientist on Earth later measures one of these particles, say particle A, they aren't causing anything to happen to particle B light years away. They are simply determining which branch of reality they are on. If they find particle A has spin up, it means they are on the branch where the universal correlation was always A up, B down. The distant particle B was always down on this specific branch from the very moment of the split. There is no faster-than-light communication because there is no communication at all, just the revelation of a pre-existing fact about your local branch of the multiverse. The spooky action is an illusion created by our single-branch perspective. From the God's eye view of the entire wave function, everything is perfectly local and deterministic, with no laws of physics broken. This reframing transforms entanglement from a paradoxical connection through space into a profound connection through the branching structure of reality itself. The particles are not whispering to each other across the void. They are silent twins, forever bound by the history they share in a specific family of universes. Their seemingly coordinated behavior is simply the result of them being on the same page of a much larger cosmic story. A story that was written in full the moment they came into existence. This elegant solution removes the troubling specter of faster-than-light influences, offering a more complete and logically consistent picture of how our quantum world truly operates. So if these parallel universes are out there, forever separated from us by the irreversible process of decoherence, how could we ever hope to find tangible proof? The answer might not lie in building a portal to another dimension, but in carefully examining the oldest photograph we have of our own cosmos, the cosmic microwave background radiation. This faint, cold light is the afterglow of the Big Bang, a snapshot of the infant universe when it was just 380,000 years old, and it blankets the entire sky. For cosmologists, it is a treasure map, and some believe it might contain the subtle, ghostly imprints of a collision with a neighboring universe bubble from an unimaginably long time ago. To understand how such a collision could leave a mark, we need to revisit the theory of eternal inflation and the bubble universe model. Imagine our universe is one stable bubble of true vacuum, slowly expanding within a much vaster, eternally inflating background of high-energy false vacuum. Now, imagine another bubble nucleating somewhere else in this frothing multiversal sea. These bubbles would expand at incredible speeds. If two bubbles formed relatively close to one another, their expanding walls could eventually meet. What would happen at that moment of contact? The physics is complex, but models suggest the collision would send a tremendous shockwave rippling through the interior of both bubbles. This shockwave would compress matter and energy, creating a distinct and potentially observable signature in the structure of each universe. Now, fast forward in our universe to the moment it becomes transparent, 380,000 years after its own bubble nucleated. The shockwave from a long-ago bubble collision would have traveled across the cosmos, leaving an imprint on the distribution of matter and energy that was just freezing into place. This imprint would then be permanently etched into the pattern of the cosmic microwave background. Researchers conducting this cosmic detective work are searching for specific, anomalous patterns in the CMB temperature data. A collision wouldn't produce a random smudge. It would likely create a distinctive, circular type pattern with a very specific temperature profile. Imagine a series of concentric rings on the sky where the temperature is slightly different from the surrounding area, like a bruise on the surface of the early universe. The key is that this pattern would be statistically unusual, breaking the generally random and homogeneous distribution of hot and cold spots that we see across the rest of the microwave background. This is not just speculative fiction, it's a serious field of research. Teams have meticulously analyzed data from satellites like Planck, which map the CMB in exquisite detail. They run sophisticated algorithms designed to scan the entire sky, searching for any signatures that match the predicted profile of a bubble collision. A few years ago, there was a surge of excitement when researchers identified several candidate regions in the Planck data that appeared to have some of the expected features. These spots were colder than their surroundings and had a circular asymmetry that made them stand out. However, upon deeper statistical analysis, the scientific consensus was that these anomalies were likely just that rare statistical fluctuations in the random noise of the CMB. They were intriguing but not conclusive proof. The search is far from over. The fact that we haven't found definitive evidence yet doesn't mean the theory is wrong. It might simply mean that our observational tools aren't yet sensitive enough, or that the most telling collisions are hidden in the polarization data of the CMB, which is more difficult to measure with precision. Future missions designed with even greater resolution and sensitivity will continue this hunt. They will be looking for that one unmistakable signature, a pattern so clear and so perfectly matched to the theoretical predictions that it could only be explained by a violent encounter with another cosmos in the extreme infancy of our own. Finding such a mark would be a monumental discovery, providing our first empirical evidence that we are not alone in the grandest sense possible, that our universe is just one island in an infinite archipelago of reality. This astonishing idea of quantum bubbles birthing entire cosmos leads us to one of the most extreme and powerful objects in existence, the black hole. These cosmic monsters, once thought to be merely the final graves of massive stars, might actually be something far more profound, cosmic engines of creation. Some of the most daring theories in physics now suggest a connection so profound it redefines our understanding of both life and death in the universe. The possibility that a black hole could be the womb for a new universe, a process deeply intertwined with the quantum bubbling of spacetime we've been exploring. To see how this could work, we have to venture right up to the very edge of a black hole, to the point of no return known as the event horizon. From the outside, this boundary is a one-way street. Anything that crosses it, including light, is lost to our universe forever, its information seemingly obliterated in the crushing gravitational singularity at the center. This presents a huge problem known as the black hole information paradox, which suggests that the fundamental quantum information about what fell in is destroyed, violating a core principle of quantum mechanics. But what if that information isn't destroyed? What if it simply goes somewhere else? This is where the theory takes a breathtaking leap. Some physicists, like the renowned Lee Smolin, have proposed the radical idea of cosmological natural selection. It suggests that the singularity at the heart of a black hole might not be a point of infinite density and the end of physics, but rather a bridge, a cosmic bottleneck where the extreme conditions trigger a quantum bounce. In this scenario, the collapse of matter in our universe could be the big bang for a new, baby universe that forms on the other side of the singularity. This new universe would exist in its own spacetime, completely disconnected from our own, but it would inherit its fundamental physical constants from the black hole that spawned it, with perhaps tiny random variations. In this wild evolutionary picture, black holes are the reproductive organs of the cosmos, and universes that are good at making stars that collapse into black holes are the ones that produce the most offspring, potentially explaining why our universe seems so finely tuned for producing these very objects. Another compelling link comes from the holographic principle, a revolutionary concept born from string theory. It suggests that all the information needed to describe a three-dimensional volume of space, like everything inside a black hole, can be encoded on its two-dimensional boundary, the event horizon. It's like a cosmic piece of holographic film where a three-dimensional image is stored on a flat surface. If this is true, then the information about every star, planet, and person that falls into a black hole isn't lost. It's smeared across the surface of the event horizon. When a black hole eventually evaporates over eons through Hawking radiation, what happens to that information? One incredible possibility is that this encoded information becomes the seed for a new reality. The evaporation and dissolution of the black hole in our universe could be the inflationary birth cry of a new universe in another realm, with the holographic data on the horizon providing the initial conditions for its laws of physics. This connects directly back to the quantum bubbles we discussed earlier. The intense, chaotic energy at the singularity of a black hole or at its event horizon could be the ultimate catalyst for a vacuum fluctuation. Remember, empty space is not empty. It's a quantum foam fizzing with potential. The unimaginable gravitational energies present could catalyze the formation of an exceptionally large and stable quantum bubble, a pocket of space-time that tunnels into a new vacuum state. This bubble would then be propelled into its own inflationary expansion, pinching off from the space-time of the black hole's parent universe to become a separate, expanding cosmos. In this view, a black hole isn't a dead end, it's a portal. The very act of gravitational collapse provides the immense energy required to nucleate a new universe from the quantum foam, making black holes the most powerful and natural generators of cosmic bubbles in the multiverse. The implications of this are truly staggering. It suggests a cyclical or fractal structure to reality that is almost beyond comprehension. Our own universe, with its hundreds of billions of galaxies, each containing billions of stars and potentially even more black holes, might itself be the interior of a black hole residing in a much larger parent universe. And each black hole within our cosmos could contain an entire fledgling universe within it, each with its own unique physical laws. This creates a picture of a grand, multi-layered multiverse, a cosmic matryoshka doll of realities nested within realities, all connected through the gravitational wombs of black holes. It transforms these objects from terrifying voids into perhaps the most creative engines in all of existence, the crucibles where the laws of physics are forged and where new cosmic stories begin. This relentless branching and bubbling of reality presents us with a profound and deeply personal question. Why are we here to witness any of it? Out of all the infinite possibilities, why does our particular universe seem so perfectly, almost miraculously, suited for the existence of complex life? This puzzle is known as the fine-tuning problem, and the many worlds interpretation offers what might be the most elegant and natural solution we have ever conceived. Consider the fundamental constants that govern our reality: the strength of gravity, the power of the electromagnetic force, the mass of a proton. These are not values derived from some grand, overarching theory. They appear to be arbitrary numbers, and yet, if they were different by even a minuscule amount, the universe as we know it would be impossible. If gravity were slightly stronger, the universe would have collapsed back on itself moments after the Big Bang. If it were slightly weaker, matter would never have clumped together to form stars and galaxies. If the nuclear strong force were a fraction less powerful, hydrogen would be the only element in existence, and the complex chemistry required for life could never arise. The list of these cosmic coincidences is long and staggering. It feels as if the universe won a lottery with odds so astronomical they defy comprehension. The traditional response to this has often drifted into the realm of theology or intelligent design, suggesting a creator who set the dials just right. But the many worlds interpretation, coupled with the idea of a quantum bubble or inflationary multiverse, provides a powerful scientific alternative that requires no designer. It is known as the anthropic principle. In its simplest form, the anthropic principle states that we can only observe a universe that is capable of producing us, the observers. This isn't an explanation in itself, but rather a selection effect. If you are dealt a hand of cards, you shouldn't be surprised to be holding a valid poker hand. The very act of you holding cards presupposes that they follow the rules of the game. Now apply this to the multiverse. If the many worlds interpretation is correct, and if the process of eternal inflation or quantum bubble nucleation creates a vast, perhaps infinite, ensemble of universes, then every possible combination of physical constants and laws will be realized somewhere. The vast, overwhelming majority of these universes will be stillborn or barren. Some will flash into and out of existence in an instant. Others will expand forever as empty, cold voids, their forces too weak to ever coalesce into atoms. But in a tiny, tiny fraction of these universes, the numbers will, by pure random chance, line up in just the right way to allow stars to ignite, planets to form and chemistry to become biology. In those exceptionally rare universes, observers will eventually evolve and look up at the sky, and they will be astonished at how perfectly tuned their home seems to be. They will marvel at the incredible luck that led to their existence, completely unaware that they are simply the inevitable inhabitants of one of the few branches of reality where such marveling was even possible. This completely reframes the fine-tuning problem. We are not winners of an impossible lottery. We are the necessary result of a cosmic statistics game with an infinite number of tickets. Our universe isn't fine-tuned, it's self-selected. We shouldn't ask, why is our universe so perfectly suited for life? But rather, in which of the infinite universes could life arise to ask that very question? The answer, of course, is this one. The many worlds interpretation doesn't make our existence any less special from our own perspective, but it does remove the need for a mysterious external tuner. The fine-tuning is an illusion born from our limited viewpoint, a perspective that is naturally restricted to only those rare branches of the multiverse where the conditions for perspective exist at all. This leads us to one of the most controversial and mind-bending thought experiments born from the many worlds interpretation, the idea of quantum suicide and its seemingly inevitable consequence, quantum immortality. The setup is deceptively simple, but its implications are profound enough to challenge our very understanding of life, death, and conscious experience. Imagine a device, perhaps a gun pointed at your head, that is triggered by a single quantum event. This could be the decay of a specific radioactive atom within a 1-hour period, an event that quantum mechanics tells us has a precise 50% probability. The apparatus is set so that if the atom decays, the gun fires. If it does not decay, the gun does nothing. You, the experimenter, agree to press the button and initiate the experiment once every minute. From the perspective of the many worlds interpretation, at the moment of each trial, the universe splits. In roughly half of the resulting branches, the atom decays, the gun fires, and that version of you dies. But in the other half of the branches, the atom does not decay, the gun remains silent, and you survive. Now you press the button again 1 minute later, and the universe splits again. In the branches where you are still alive, this process repeats. After 1 hour, an outside observer would see a gruesome spectacle. From their single universe perspective, the odds of you surviving 60 consecutive 50-50 trials are astronomically small, essentially zero. They would almost certainly find you dead. But what is the experience from your point of view inside the experiment? If many worlds is correct, your conscious experience is tied to the branches where you continue to exist. At every single split, there is always a branch where the quantum dice roll in your favor. After 1 minute, you are alive. After 1 hour, you are still alive, having witnessed the gun fail to fire 60 times in a row. After 1 year, you would have seen it fail over 500,000 times, a sequence of events so statistically improbable it borders on the miraculous. From your first-person perspective, it would appear as if you cannot die from this experiment. You would achieve a form of involuntary immortality, at least from this specific cause of death. Your continued existence wouldn't be a miracle. It would simply be the necessary consequence of only being able to have a conscious experience on the branches where you are alive to have it. This thought experiment is not a proposal for achieving eternal life. It's a stark illustration of the subjective nature of probability and consciousness within a branching reality. It highlights a key difference between the Copenhagen and many worlds interpretations. In Copenhagen, the wave function collapses, and after enough trials, you are almost certainly dead. The probability has played out. In many worlds, probability isn't about what will happen, but about which branch you will find yourself on. Your subjective experience is guaranteed to be one of survival, because the branches where you die are branches you cannot experience. However, this idea is riddled with serious logical flaws and is widely rejected by physicists and philosophers. even those who support the many worlds interpretation. The first major flaw is its reliance on a privileged notion of consciousness. The experiment assumes that your consciousness somehow follows the branches where you survive, as if it were a soul hopping between realities. But most modern interpretations of consciousness suggest it is an emergent property of a physical brain. In the branches where you die, that specific brain ceases to function, and that stream of consciousness ends. There is no transfer, it simply stops. The you in the surviving branch is a separate consciousness from the one that died, even though you both shared a common past. You wouldn't feel immortal, you would just be the one copy that got lucky every single time, while countless other versions of you met instant ends. Secondly, the experiment offers no protection against non-quantum death. You might be immune to the quantum gun, but you are not immune to old age, disease, or a heart attack. The experiment doesn't grant immortality. It only suggests that for this specific quantum-triggered cause of death, there will always be a branch where you avoid it. Furthermore, the idea becomes absurd when scaled. Would you also survive a nuclear explosion if its trigger were quantum? The many worlds interpretation doesn't allow for magic. If an event would destroy your brain in every possible way, then every branch resulting from that event would contain a dead version of you. There is no branch for a conscious experience to continue in. The thought experiment only works for clean, instantaneous deaths that leave a potential branch open for a functioning brain to persist. Ultimately, quantum suicide is less a practical proposal and more a powerful philosophical tool. It forces us to confront the bizarre implications of taking a subjective, first-person viewpoint within a branching multiverse. It starkly demonstrates that what we experience as probability might actually be a measure of the plurality of existence. While we should firmly relegate the idea of actually conducting such an experiment to the realm of dark thought exercises, it successfully underscores a profound point. In a many-worlds reality, your personal story isn't defined by a single narrative, but by the specific path you take through an infinite tree of possibilities, a path that, by its very nature, is the only one you will ever know. This fascination with branching realities has exploded far beyond the pages of physics journals, deeply embedding itself into the very fabric of our culture. From the sprawling multiverse of Marvel superheroes to the existential horror of Rick and Morty's infinite dimensions, the idea that we are not alone in the grandest sense possible has become a staple of modern storytelling. These narratives tap into something primal within us, a deep curiosity about the road not taken and the haunting question of what might have been. They allow us to explore fantastical versions of ourselves, to see our lives reflected through a funhouse mirror of infinite possibilities, and that is an incredibly powerful and relatable hook for any audience. Yet, while these creative explorations are thrilling, they often propagate some significant misconceptions about what the physics actually suggests. One of the most common mix-ups is the idea of travel between these worlds. In films and television, characters frequently hop between universes using some intricate device or portal, often encountering and even battling their alternate selves. This makes for fantastic drama, but from a physics standpoint, it's likely pure fantasy. Remember the process of decoherence. The very mechanism that creates the branches also permanently severs their connection. These worlds aren't like different countries on a map that you can sail between. They are more like separate, non-overlapping pages in an infinite book. There is no known physical bridge, no wormhole or energy field that could connect two decoherent branches of the wave function. The laws of physics that govern causality and information flow are locked within each individual universe, making crossover a violation of those very laws. Another popular trope is the notion of a prime universe or a central timeline from which all others diverge. This is a narrative convenience, giving audiences a home base to return to, but it doesn't align with the democratic nature of the many worlds interpretation. In Everett's view, no branch is more real or more fundamental than any other. The universe where you decided to wear a blue shirt today is just as real as the one where you chose a red one. There is no original copy, there is only the endlessly dividing tree with every branch possessing equal validity. This can feel unsettling as it removes our universe from any position of cosmic privilege, but it is a core and perhaps the most humbling aspect of the theory. These stories also tend to focus on massive, life-altering decision points as the source of branching, winning the lottery, becoming a superhero, or causing a global catastrophe. While these macroscopic events are certainly the result of branching, their origin is far more mundane. The split begins at the quantum level with the seemingly insignificant fate of a single particle. The grand divergence between a world at peace and a world at war might ultimately stem from a quantum fluctuation that influenced a single neuron in a single leader's brain at a critical moment. The branching is constant and microscopic, and the dramatic macroscopic differences we see in fiction are simply the amplified consequences of trillions of these tiny splits accumulating over time. Perhaps the most important clarification is that these parallel worlds are not other dimensions in some mystical sense. The term dimension often gets misused in pop culture to mean a parallel realm. In physics, dimensions are the fundamental facets of our spacetime: length, width, height, and time. The branches of the many worlds interpretation don't exist in a different dimension. They are all part of the same high-dimensional reality, but have become decohered and thus inaccessible to one another. They are right here, superposed with our own, but we are forever isolated on our specific thread of history. Despite these misconceptions, the cultural embrace of the multiverse is far from a negative thing. It serves a vital purpose by introducing these mind-bending concepts to a massive audience, sparking curiosity and wonder that can lead to a deeper appreciation of real science. A viewer might watch a show like Devs or Everything Everywhere all at once and for the first time start asking genuine questions about quantum mechanics and the nature of reality. This cultural conversation creates a bridge, allowing scientists and educators to step in and say, "That was a fascinating story. Now let's talk about what the math actually says." It turns abstract theory into a relatable narrative, providing a gateway to a more nuanced understanding. This synergy between science and fiction doesn't dumb down the concepts. It amplifies their reach, ensuring that the most profound questions about our existence continue to captivate and inspire generations to come. Accepting the many worlds interpretation isn't just a philosophical shift. It fundamentally rewrites the rulebook for how physicists approach the most profound problems in their field, particularly the quest for a theory of quantum gravity and the grand unification of all forces. The traditional approach to these problems, often rooted in the Copenhagen interpretation, is burdened by the need to explain the mysterious collapse of the wave function, an event that seemingly violates the smooth, deterministic evolution described by the Schrödinger equation. This creates a glaring paradox at the heart of physics. Our most fundamental theory has a special ad hoc rule that only applies when something is being measured, a term that is never clearly defined. This isn't just a minor inconvenience, it's a major roadblock. How can you develop a complete theory of the entire cosmos if your equations require an external observer to make them work? Who observes the universe to cause its wave function to collapse? The many worlds interpretation elegantly dismantles this roadblock by simply removing it. It asserts that the wave function never collapses, it just relentlessly and deterministically evolves, branching as it goes. This clean mathematical purity is incredibly liberating for theorists. It allows them to take quantum mechanics utterly seriously as a description of the entire universe, not just tiny parts of it observed from the outside. This perspective is crucial for quantum cosmology, the attempt to apply quantum rules to the origin of the universe itself. In a many-worlds framework, the entire cosmos can be described by a single universal wave function that has been branching since the first moment of time. There's no need to invoke a mysterious observer outside of space-time. The universe simply exists in a superposition of all possible histories, each one complete and self-consistent. This makes the problem of quantum gravity conceptually cleaner, if not mathematically easier. Theorists can focus on solving the hard equations of how space-time emerges from a quantum description without the added, perplexing burden of figuring out when and how those equations suddenly stop working. This shift in perspective also profoundly influences how we think about the nature of space-time and information. The black hole information paradox, a 50-year-old puzzle, highlights the tension between quantum mechanics and general relativity. It suggests that information about what falls into a black hole is permanently lost when the black hole evaporates, which violates the quantum principle that information must always be preserved. The many-worlds view offers a radical solution. The information isn't lost, it's just transferred to another branch of the wave function. From the perspective of our branch, the information seems to vanish. But from the God's eye view of the entire multiverse, it is perfectly conserved. This suggests that the key to resolving the paradox lies not in modifying quantum mechanics or gravity in our single universe, but in understanding how information flows between decoherent branches. It reframes the problem, pushing physicists to consider a more holistic, multiversal structure for reality where information conservation is global, even if it appears local from our limited vantage point. Furthermore, the dream of a theory of everything, a single framework that unifies quantum mechanics with general relativity, looks different through the many-worlds lens. In the Copenhagen view, such a theory would have to somehow include a definition of measurement and a mechanism for collapse. In the many-worlds view, the theory only needs to describe the unfettered evolution of the wave function. This has led to increased interest in formulations like quantum Darwinism, which explains how our classical, objective reality emerges through the process of decoherence and the proliferation of information into the environment. It's not that the moon isn't there when you aren't looking. It's that its existence has been recorded by countless photons and particles, creating a stable, branching history where the moon is always there. This approach seeks to derive the classical world from the quantum one, rather than assuming a baffling boundary between the two. Ultimately, embracing many worlds transforms physics from a science focused on predicting outcomes in a single reality to a science that seeks to map the entire structure of the multiversal wave function. It changes the questions we ask. Instead of what outcome will we see, the question becomes what is the complete entangled structure of reality. This doesn't make the physicist's job easier, but it does make it more coherent. It provides a stable, logical foundation upon which to build our understanding of the cosmos, from the smallest strings to the largest cosmic bubbles, all within a single, elegant, and breathtakingly vast mathematical framework. The hunt for evidence of these other realities is accelerating, moving from philosophical speculation into the realm of hard, observational science. The next decade promises a revolution in our ability to probe the very edges of reality, with powerful new telescopes and unprecedented quantum technologies acting as our multiversal detectives. The first major frontier in this search remains the cosmic microwave background, that ancient echo of the Big Bang. While current data from the Planck satellite hasn't yet delivered a smoking gun for a bubble collision, the next generation of observatories will peer deeper than ever before. Missions now in advanced planning stages will map the CMB's polarization, the specific direction of its light waves, with exquisite precision. This polarization data is a cleaner record of the primordial universe, less muddied by later galactic events. A collision with another universe bubble would create a distinct, swirling pattern in this polarization, a unique fingerprint that would be incredibly difficult to explain by any standard cosmological process. Finding such a signature would be a watershed moment, providing our first tangible glimpse of a cosmos beyond our own. Beyond the CMB, astronomers are also turning their gaze to the large-scale structure of the universe itself. The distribution of galaxies and galaxy clusters across billions of light years is not perfectly random. It holds faint imprints from the universe's earliest moments. Sophisticated sky surveys, like those conducted by the Rubin Observatory, will map the positions and motions of millions of galaxies. By analyzing these vast cosmic maps, scientists can search for other types of anomalies that might hint at a multiversal origin. For instance, if our universe experienced a gentle tug from a neighboring bubble in the distant past, it could have left a subtle directional preference in the way galaxies are moving on the largest scales, a kind of cosmic current that shouldn't exist in an entirely isolated universe. Discovering such a preferred direction would force us to radically reconsider our place in the greater cosmic architecture. On the quantum side, the evidence is becoming increasingly indirect yet compelling, thanks to the rapid advancement of quantum computing and control. The very existence of increasingly powerful quantum processors is, for many physicists, a form of evidence in itself, as these machines tackle problems that are demonstrably impossible for any classical computer to solve in the age of the universe. The most straightforward explanation is that they are harnessing the computational resources of parallel branches of reality. But the next phase of research goes beyond mere operation. Physicists are designing experiments that probe the precise moment of decoherence, the split itself. By creating larger and larger objects in a state of quantum superposition, like tiny vibrating drums or even specially designed viruses, and then meticulously measuring how and when they decohere, researchers can test the predictions of the many worlds interpretation against its rivals. If the transition from quantum weirdness to classical certainty always matches the many worlds model of branching rather than a sudden collapse, it will powerfully bolster the case for a multiplying multiverse. Perhaps the most tantalizing future experiments involve the search for any residual communication between these branches, however faint. While decoherence suggests branches are forever isolated, some speculative theories propose that under extremely specific conditions, a minuscule amount of information or influence might still be exchanged before the separation is complete. This wouldn't be a phone call to another universe, but more like detecting a faint, ghostly echo. Experimentalists are dreaming up incredibly sensitive schemes to look for these effects, perhaps by creating two massive, entangled systems and watching to see if any unexpected correlations appear that can't be explained by standard quantum theory. Finding even a whisper of such an effect would shatter our current understanding and open an entirely new field of physics dedicated to multiversal interactions. Each of these avenues of research, from the cosmic to the quantum, brings us closer to answering the ultimate question: are we the sole outcome of a cosmic accident, or merely one thread in an infinite and ever-growing tapestry of existence? Despite its elegant solutions, the many worlds interpretation is far from universally accepted, and many physicists raise serious and thoughtful objections to its breathtaking claims. The most common critique is often summed up by the principle of Occam's razor, the philosophical idea that the simplest explanation is usually the best. Critics argue that many worlds is the ultimate violation of this principle. Instead of finding a simple, economical solution to the measurement problem, it postulates an astronomical, indeed infinite, number of entirely new universes. From this perspective, it seems like an extravagant, almost absurdly wasteful solution, multiplying entities far beyond necessity. Why invent an infinite number of unobservable worlds just to avoid the weirdness of wave function collapse? Proponents counter that this is a misunderstanding of Occam's razor, which favors simplicity in the foundations of a theory, not in the consequences. They argue that many worlds is actually simpler at its core because it requires no extra rules or processes, just the single, smooth, deterministic evolution of the wave function as described by the Schrödinger equation. The infinite branching is not an assumption but a prediction of taking that single equation seriously. The real complexity, they suggest, lies in the Copenhagen interpretation's need for an ill-defined collapse mechanism and a mysterious division between the quantum and classical realms. Another major objection is the charge of non-testability. If these other worlds are truly disconnected and unobservable, can the many worlds interpretation even be considered a scientific theory? Science, by its nature, relies on empirical evidence and the ability to falsify a claim. If there is no conceivable experiment that could prove these other branches don't exist, then isn't the theory more of a metaphysical stance than a physical one? This is a powerful criticism that even supporters grapple with. Their response often points to the indirect evidence we've discussed, like the success of quantum computing and the detailed predictions of decoherence theory. They argue that while we may never directly observe another branch, the theory makes specific, testable predictions about how quantum systems behave in our branch as they decohere. Furthermore, if a theory like eternal inflation is confirmed through a bubble collision signature in the CMB, it would provide strong circumstantial evidence for a broader multiverse, making the idea of branching within our own universe feel less far-fetched. The debate hinges on whether this indirect support is enough or if a theory must be directly falsifiable to be considered scientific. Perhaps the most technical and stubborn problem for many worlds is the issue of probability. In standard quantum mechanics, the wave function doesn't just describe possibilities, it assigns precise probabilities to them. We can say an electron has a 90% chance of being measured here and a 10% chance of being measured there. But if many worlds is correct and both outcomes definitively happen, what does it even mean to say one is 90% probable? From a God's eye view, both branches are equally real. So why do we, in our branch, observe outcomes that align with the high probability predictions? Why do we almost always find ourselves on a branch where the quantum dice roll in a way that matches the Copenhagen statistics? This is known as the problem of defining the measure of a branch. Advocates have proposed complex solutions, often involving the amplitudes of the wave function, suggesting that while all branches are real, they are not all equally weighted. You are more likely to find yourself in a branch with a high amplitude, which corresponds to the high probability outcome. However, turning this intuitive idea into a rigorous mathematical definition that recovers the standard rules of probability has proven to be a formidable challenge and remains an active area of research. Given these substantial objections, it is crucial to remember that the many worlds interpretation is just one of several competing explanations for quantum weirdness. The oldest and long dominant view is the Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s. This interpretation draws a sharp line between the quantum world of tiny particles and the classical world of measuring devices and observers. It states that a particle exists in a blurry superposition until it is observed or measured, at which point its wave function collapses into a single, definite state. The act of measurement is fundamental and irreducible. While successful for making predictions, Copenhagen is often criticized for its vagueness. It provides no clear definition of what constitutes a measurement. Does it require a human consciousness, a photographic plate, or a cat? This reliance on an undefined external observer makes many physicists uncomfortable, as it seems to place human consciousness at the center of physics and offers no explanation for how the collapse actually occurs. It simply posits that it does. A fascinating and visually intuitive alternative is the pilot wave theory, originally proposed by Louis de Broglie and later developed by David Bohm. This theory, also known as Bohmian mechanics, is explicitly deterministic. It says that particles are not probability clouds but are real, point-like objects that always have definite positions. However, they are guided by a pilot wave, a real physical field described by the wave function. This wave moves through space and influences the particle's trajectory. The famous double-slit interference pattern emerges not because a single particle goes through both slits, but because the pilot wave goes through both, creating a complex guidance pattern that directs the particles to build up the pattern over time. This theory completely eliminates wave function collapse and the need for an observer, offering a clear, objective reality. However, it comes with its own baggage. The theory is explicitly non-local, meaning the pilot wave can influence a particle instantaneously across any distance, a feature that makes it incompatible with the spirit of Einstein's relativity, even if it doesn't technically violate it by allowing faster-than-light signaling. A more recent class of alternatives are objective collapse models. These theories propose that the wave function collapse is not triggered by measurement, but is a real, physical process that happens spontaneously when a system becomes too large or massive. In these models, the Schrödinger equation is slightly modified to include a tiny, random collapse term. For a single electron, this term is negligible, and the particle can happily exist in a superposition. But for a macroscopic object like a cat or a measuring device, the random collapses quickly add up, forcing the object into a definite state. This provides a clear, objective threshold between the quantum and classical worlds without needing an observer. The challenge for these models is that the modified equations are ad hoc. They are added to make collapse happen rather than being derived from more fundamental principles. Furthermore, to avoid conflict with existing experiments, the collapse effect must be incredibly weak, making it very difficult to test directly, though researchers are actively designing experiments to try and detect it. Each of these interpretations, Copenhagen, pilot wave, objective collapse, and many worlds, solves some aspects of the quantum mystery while creating new puzzles of its own, leaving physicists to choose which set of philosophical dilemmas they find most palatable in our quest to understand the fundamental fabric of reality. So we've journeyed from the flickering uncertainty of a single electron to the birth cries of entire cosmos, all connected by the astonishing idea that reality is not a single, static stage but a living, breathing, and endlessly dividing tree of possibility. We've seen how the bizarre rules of the quantum world don't just apply to tiny particles in a lab, but might very well be the engine of existence itself, constantly spawning new universes with every passing moment. This isn't just a minor tweak to our worldview, it's a complete and total transformation. It redefines the meaning of you, of choice, and of reality itself, suggesting that every road not taken is in fact being traveled right now by another version of you living a life just as real and vivid as your own. This radical vision challenges us to see ourselves not as isolated individuals on a single path, but as a focal point in a vast, shimmering network of potential. It asks us to find significance not in being the one unique story, but in the rich, personal experience of the story we are actually living. The warmth of the sun on your face, the love you feel for your family, the awe you experience when gazing at the stars, none of that is diminished by the existence of other possibilities. If anything, it's magnified because it highlights the incredible, beautiful uniqueness of your personal journey through the multiverse. You are the universe experiencing itself, and in this branch you are here right now pondering its deepest mysteries. As we reach the end of our exploration, I want to leave you with one final, fun thought to carry with you. If you could peer across the vast, decoherent branches of the multiverse and step into one other reality for just a single day, which one would you choose? Would you visit the universe where you pursued that childhood dream career, or the one where a different historical event changed the entire course of human culture? Would you seek out a world with slightly different laws of physics, just to see what a blue sun looks like or to experience what true silence sounds like? Let your imagination run wild with the infinite possibilities. I'd love to hear which parallel universe captures your curiosity. Share your most creative ideas down in the